It's chemistry time! Today we're talking about chemical and physical changes and properties along with pure substances and mixtures. By the end of this video, you should be able to explain the difference between chemical and physical properties and changes, in addition to some pure substances, definitions, and mixtures. So for today's timeline, we're going to first review matter and some words that are common to matter. If you haven't seen that video yet, please click on the link in the description below to get caught up on those terms. We're then going to move on to properties and changes. So physical chemical properties, physical chemical changes, and then a demo showing the difference between the two by dissolving and melting sugar. Finally, we're going to wrap it up with some pure substances and mixtures as definitions and applications to identify the mixtures that I'm going to show you. So then, what is matter? If you did not see my previous video, anything that takes up space and has mass is matter. Therefore, you matter. Aww. Which you do. You truly do. You do matter. And matter is basically a fancy word for stuff. It's the stuff that makes up all the other stuff. So in chemistry, when we're talking about the stuff that makes up all the other stuff, we're talking about atoms. And if we have an atom composed of protons, neutrons, and electrons, and we have more than one atom bonded together, we now have a molecule. And if we have two different kinds of atoms or more bonded together, we now have a compound. So those different ways of arranging our atoms also make up matter, which is everything. It's all the stuff. Now, matter has chemical and physical properties, but it also can be changed chemically and physically. So these two categories are what we're talking about today. We're talking both about the chemical and physical properties, which are kind of like the personalities of matter, and we're also talking about the chemical and physical changes that can happen to matter. So physical properties, those personalities we talked about of matter, are basically anything that's behind my head right here. So physical properties could include color, shape, mass, volume, boiling point, melting point, magnetism, weight, its mass, the state of matter it's in, the texture, is it soft, is it squishy, its solubility, its dissolvability. Again, if you haven't seen my videos on solubility, please click on the link in the description below to see those. Other things such as malleability, the ability to bend metal, for example, back and forth, or shape it into something we would like to. Those are all physical properties of matter. So here's kind of a generalized list of physical properties that include the following, but not limited to. There's many, many more. Basically, anything you can see with the naked eye or a magnifying glass is included in physical properties, personalities of matter. Whether the object is magnetic, whether it's soluble, it's dissolvable, the state that it's in, the color that it is, how heavy or light it is, its weight, and whether it's rigid or malleable. You could even include your senses, right? So your sense of smell, if it smells pleasant like a rose or a daisy, or if it smells nasty like a fart. You don't want to necessarily smell a nasty fart, but that would be a property of a fart. They tend to stink. Anything that can be physically measured is a physical property. If you can take a ruler and measure the length or the dimensions of matter, it's a physical property. If you can put the matter on a scale, that's a physical property. It's the weight of that matter. Here's kind of a simplified list that applies to you directly. Your height, how tall you are, your weight, and your eye color. Those are all things you can think about that are your physical properties of you as matter. Because as we mentioned before, you matter. So you have your own physical properties. There are also physical changes. When we can change something physically, it's typically by changing its state. Now, I'm not saying like how we just moved from Arizona to Virginia. We're not talking that kind of change of state. We're talking a change of state of the chemical, of the matter. In other words, if you can change it from a state that's a solid to a state that's a liquid to a state that's a gas, those are typically reversible changes. Therefore, they are physical changes. A physical change is typically reversible, and it does not change the identity of the substance. For example, if we were going to take some water and put it in the freezer, it would freeze and become ice. That ice cube is still water. You haven't magically converted the water to a different chemical. It's not now magically become wine in the freezer. I wish. But that's not how it happens, right? So water is still going to stay water. It's still just water. It's now in a frozen state of water. Now, if you take that ice cube out and you melt it, it is now water in the liquid state. It's still water. Again, you didn't magically convert it to Kool-Aid by melting the ice cube. It's still water. If you take that liquid water and you put it on your stovetop and you heat it up until it boils and it steams out of the pot, that steam is now just water that has been energized, and all those little energized particles of water are going to spread far out from each other, hence the steam. It's still water. You didn't magically convert the water molecule into a different chemical. It's still just water. So, if you do not change the identity of the substance, you have made a physical change. All right, here we are in my kitchen, and we are going to boil some water. Wait a sec. Kimber, you're not wearing any lab gear. You're not wearing any lab gear. Oh no. Safety first, always. Kimber, come here. Penny. Yeah? Is this time yet? Is this time yet? That's a good girl. Good girl. Is this time yet? Good girl. Is this time yet? Safety first. Safety first. We're gonna protect those beautiful eyes, huh? Yes, we are. Yeah. Yeah. Already we can see that the water is steaming. The water is steaming because we are adding heat from the stovetop. The water was in liquid form previously and is now starting to bubble. It's still water. Nothing has changed. It is still water. The steam that you are seeing, that is water. It's water vapor coming out of the liquid water. So what we're seeing up here, and the reason why this can burn you, is because this is water at 100 degrees Celsius. So that is water that's really, really hot. That's the boiling point of water. Hence the reason why it's now boiling. This steam is water molecules moving really fast and far apart from each other. And in fact, to show you that this is still water, this steam right here is still water. Nothing has changed about the chemical itself. It's still water. So, in order to show you that, it's reversible, hence a physical change, being that nothing has changed about the water except its state. Let's try and condense this water back. So hopefully what you can see is that there's little water droplets forming on the glass. The glass is cooler, so as the steam hits the glass, you can see the water condenses back into a liquid state from a gaseous state. And that is a physical change. So evidences of physical changes then are basically that nothing seems to change the physical properties of the object. So that list of physical properties we talked about, the color, the texture, the weight, the magnetism, all those things, if those don't seem to change, it's probably a physical change, depending on what you did to the matter. For example, if we have two magnets, and we can see that the two magnets are magnetic to each other. So before I do anything to them, just two normal magnets magnetize to each other before I do anything. Now if I took a glass of water, oh check that out, look at my mouth. So if we take a glass of water and we put one of these magnets into the glass of water, and we wanted to know, hey, did this change the magnet? Is the magnet now intrinsically different because I put it in the water? Well, if it was magnetic before, and then I did something to try and change it, and if it's still magnetic afterwards, which it clearly is still magnetic afterwards, then we know this must have been a physical change. The magnet did not intrinsically change. It's still magnetic, whether it was in the water or not. Doesn't matter. How about this one? If we have something that's yellow, like say this yellow Post-it note right here, if we took this yellow Post-it note and I was going to do something to change it, like say rip it in half. I've ripped it in half and it's still yellow. Its physical property is still yellow. I haven't changed the Post-it note by ripping it. It's not now magically become pink or magically become magnetic or something afterwards. It's still just a yellow Post-it note. It's a physical change. Another example for this is that if it dissolves in water, it can be pulled out of the water in its original state. Now, this is kind of hard to visualize, and I know not a lot of people have tried this. So I want to demonstrate this for you in my kitchen. So let's see this in action. Salt dissolving in water is also a physical change. The water has not changed its property, and neither has the salt. Now we're going to prove that by dissolving some salt in water. So I've got some salt in my salt shaker, got some water, stove is still a little hot. So we're going to take a tablespoon of salt. Here we are. And we're going to dissolve the tablespoon of salt into the water. All right. And so you can see that the salt has in fact dissolved in the water. Since this looks the same throughout, and we can't tell the difference now between the water and the salt, although we know the salt is in there, this is now a mixture. And since we can't see the difference, we would call this a homogeneous mixture or homogeneous mixture. Just like milk or ketchup. You can't tell the difference of all the other stuff that's in there. All right, so now the point I'm trying to prove is that the salt is still salt inside this water. The water is still water. So what we're going to do is boil off all the water. So I'm going to boil this pot until all the water is gone. And by the end, we should see salt still in the pan. The salt cannot just go away with the water steam. It's not going to change state like the water does. So the salt should be still left over at the bottom of this pot by the time all the water boils away. And that would be evidence of a physical change, because neither of the chemicals have truly been changed to something different.
In the sky, gazing far into the night, I raise my hand to the fire, but it's no use, 'cause you can't stop it from shining through. It's true, baby, let the light shine through. If you believe it's true.
Kimber, you want to show them all a trick? Yeah. Be still. Be still. Be still. Good girl. Good girl. Are you ready? Are you ready? Girl. By the way, if you saw my previous video about the periodic table, you would also note that I'm using a pot, and the burner here is quite larger than the pot. So you should note that the metal is actually getting really hot through thermal conductivity. So this pot is made out of metal, and you can feel the heat transfer into the handle. I don't have one of those nifty ones with the silicone grips or anything like that, so the heat that's rising from the stovetop is actually causing this handle to become pretty hot as well. Hopefully you're seeing that already, that there's a layer of salt on the bottom of the pan. We're getting pretty close to the end here, where there's not going to be much water left. Alright, now before the salt starts popping profusely and burning me, here we go. So now we have a pan, or a pot, that's got all of that salt, that tablespoon of salt, still on the bottom. This was a physical change because the salt merely dissolved in the water boiled off as steam, and we still have salt unchanged. I could still just collect this salt and eat it if I wanted to, or put it in my next recipe. It's still the same salt. The chemical has not changed. Therefore, this is an example of a physical change. Now that we're back, we can assume, in conclusion, that a physical change is a change that does not alter the physical properties of an object or of matter. How about chemical properties then? Chemical properties of matter are the properties, the personalities of a chemical. So when a chemical reaction can take place, if you're going to light TNT at some point, you could assume that a chemical reaction is going to take place. That would be a chemical property of TNT, for example. When it forms a new substance, so if you know that the chemical property is that it has the ability to form something entirely different than what you started with, that's a property of that chemical. If the material or object is flammable, if it's innately flammable, like paper, that would be a chemical property of paper or hair, which, by the way, if you've ever smelt burning hair, it's disgusting. Do not recommend. If the chemical is toxic, hazardous, corrosive, like the image above my head, that's an NFPA label. And those are chemical labels meant to identify any specific hazards of a chemical. It shows the chemical properties. It's like a giant label you can put on any kind of chemical to indicate if it's a fire hazard, if it's a safety hazard, if it's a health hazard, if it's really reactive or not. And you can see those things on basically everything. Check your pool chemicals if you have a pool next time you're out there chlorinating your pool or anything like that. Guaranteed you'll find those NFPA labels on there. Or just check under your kitchen sink. I bet you half the stuff you have under there has one of these on it and has specific chemical properties indicated by that label. If the object can rust like a nail, that is a chemical property of a nail. If the object produces light or heat, if it produces light, then you can assume that's a chemical property. Or heat, like a fire. Any property that matter or a chemical can be defined by is its chemical property. Again, we're not measuring this so much as defining the chemical itself. We are labeling that chemical, its ability to do X, Y, Z. That's a chemical property. For example, we were talking about a physical property being your... So evidence of chemical change then. Color change. If you see a color change, you know that had to be something chemical that created it. Light is produced or consumed. So you could either have light come from it or go away. That would be a chemical change. Heat is produced or consumed. Gas is produced. It bubbles or fizzes. That would be an example of a chemical change. A solid forms when you mix two liquids together. If they're miscible, they mix together and you have something precipitate out of the solution. Again, talked about that in one of my previous lessons. Please click on the link in the description below for that as well. If any of those things don't happen, so if you don't see a color change, if you don't see light, it doesn't have to be all of them. If you don't see at least one of them happen, it's likely that it was a physical change that happened, not chemical. You pretty much have to see one of those things or multiple of those things happening in order to classify it as a chemical change. So the fireworks above my head are a great example of chemical change because you have heat produced when those things explode. You have light produced. That's the joy of watching fireworks, is the fact that you can see that light being produced from a chemical change. You also see a color change. Initially, those fireworks, before they're lit, are a completely different color than the beautiful, dazzling array of colors you see in the sky. So that one is an example that includes many of our evidences for chemical change. If you want to see this really great rap over here, please click on the link in the description below and check out these two girls. They are awesome and they've got a pretty cool rap going. They're saying like, is the change chemical? Da, 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 da. It's really good. I would check it out if I was you. Let's give it a try. So if we want to identify chemical versus physical changes, let's look at these different pictures and try and pick out which ones are which. If we're looking at this apple over here, we can see that the apple is rotting, literally rotting. We want to think, has that changed chemically or has it changed physically? For a physical change, the apple itself has to be the same. I don't know about you, but I would rather eat this side of the apple than that side of the apple. The physical property of this Granny Smith apple is that it's white on the inside, but we do have evidence of a color change. Because of this color change, we can assume that this is a chemical change. Now, if you've ever bitten into a rotting apple, you would also know that this is a chemical change because these sides don't taste anything like each other at that point. How about the toast? The toast itself, we've got normal bread on this side, we've got burnt or slightly burnt toast on the other side. Is that a chemical or physical change? Let's think about this one in a different way. Could we unburn this toast? Is this toast reversible? Can we make it back to this bread state ever again? The answer to that is no. You can't take this toast and turn it back into the white bread. Because of that, and because there is a color change, just as before with the apple, we know that this has to be a chemical change as well. Let's go down to the Oreo cookies. We have two Oreo cookies, and let's say you take a hammer to it. You take a mallet to your cookies and you smash them up. Smash them up really good. Well, the cookies still taste like cookies. They're still the same in that regard. They're still the same color. They haven't changed color. They've only changed shape, but that's not such a big deal. They're still the same texture for the most part, minus a few crumbs here and there. In this case, since there's no bubbling or gas produced, there's no color change, there's no heat produced, there's no light produced, we have to say this would be a physical change. Let's jump over to the nail. We have a normal nail and a rusted nail. Immediately you should be thinking, well, that's a different color than it was in its original state. Because it's a different color, we can automatically assume this has to be a chemical change. Last but not least, we've got some shredded paper. The paper is still paper, just like the Post-it note that I ripped up earlier. It's still the Post-it note, still a yellow Post-it note. Now granted, these are a bunch of little strips of paper that would be nearly impossible to piece back together again, but the point is that you could. And because of that, it is a physical change. There was no gas produced, no heat, no light, no color change. It must be a physical change. So, I would also like to demonstrate the difference between the chemical and physical change by dissolving and melting sugar. We're going to do this in my kitchen. We're going to take 2 tablespoons of sugar and we're going to dissolve that in some water. And I want you to think, is that chemical or physical? We're also going to take 2 tablespoons of sugar and we're going to melt it in a pan, and we're going to see if that's chemical or physical as well. So think about that, and in the meantime, I'll meet you in my kitchen. All right, here we are in my kitchen again, and this time we're going to dissolve some sugar and melt some sugar and see the difference between the two. So I've got my container of sugar here. See, it even says sugar on it. And I've got a tablespoon and some water. So if I take a tablespoon of sugar, we're actually going to put 2 tablespoons in there. 2 tablespoons of sugar and water. And I stir that around. We can see that the sugar dissolves in the water. It is soluble in the water. Just like the example with the salt from before, this is a physical change. The sugar could be left in a pot if I boiled off the water just the same as the salt was. So this would be an example of a physical change. Now, if I wanted to see the difference between dissolving sugar in water versus melting sugar, we might end up seeing a different property. So we're going to take the same amount, 2 tablespoons of sugar, and we're going to put that right into my pot. Turn the stovetop on to high. We're going to try and melt this sugar in my very already hot pot. So what we can notice right now is that some physical properties of the sugar, physical properties are again things that we can measure with the naked eye. So we could say that it's crystalline. It's got maybe like a light beige color, maybe, perhaps a little light beige color to it. All right, it's starting to clump up a little bit. Interesting. So hopefully you can tell right away that melting the sugar, I now have a different color. The sugar is a different color now than what it was before. And it's kind of syrupy. So that color change would indicate a chemical change. Pure substances and mixtures is the last leg of this lesson today. Pure substances have only one chemical or molecule type present, just one. But there's a lot of them, right? There's not just one single atom. There's a lot of them. For example, you could have a whole bag of marshmallows, of these little jet puff white mini marshmallows, right? There's a whole bunch of little marshmallows in here, and it's only this one type of molecule or atom or chemical or whatever you want to describe it as. This would be a pure substance example. However, if we were going to make a mixture, let's say I wanted to take some of these marshmallows out and put it in a bowl of gummy bears. That would be 2 or more pure substances. So if I had a separate bowl of gummy bears, that would be a pure substance of gummy bears. And the second I add marshmallows, another pure substance, to the bowl, I have now made a mixture between the two. Now, mixtures are different molecules, just like marshmallows and gummy bears are different, that are not linked or bonded. Just because I poured the marshmallows on top of the gummy bears didn't suddenly make them stick together out of nowhere without adding heat or anything like that. They're just mixing around together, right? That's a mixture. Now, there are 2 types of mixtures. There's homogeneous and heterogeneous. Those 2 types are describing the different molecules that are mixed together. So for example, if we're looking in this table over here, we have pure substances. Again, that's just the one type present. So if you've got like a container of salt, that's just a whole bunch of NaCl in there, all just salt. If you've got water, If you've got a glass of water, that's still just a whole bunch of H2O molecules in there. A lot of water. If you've got a piece of aluminum foil, that's a pure substance. It's just aluminum. Now, if we want to make a mixture, I could take this same glass of water and I could pour my salt into it. Now suddenly I have made a mixture. I have added two separate pure substances to each other, and I have made a mixture. So let's go over the types of mixtures now, the two differences. Homogeneous is when it looks uniform, like one single substance. For example, the milk. So if you're looking at this down here, you can see at a molecular level that they're all kind of evenly distributed, albeit there's lots of different pieces, a lot of different pure substances, but they're all mixed together evenly. Because of this, it looks like one single substance. It's uniform throughout. Now, anybody who has been raised around cows, by the way, milk comes from cows, in case you didn't know that. If you've been raised around cows or know anything about milking a cow, you know that when you milk a cow, there's a lot of fat in the milk initially. In order to make skim milk, you basically have to wait for the fat to rise to the top of the milk. And then you skim the fat off the top of the milk. That's how you make skim milk. So milk itself is homogeneous because it's a mixture of fat, protein, liquids, pus, other things, all coming from the mommy cow. So because you can't physically see the difference with your eyes, and it looks like milk is just a white liquid throughout, you would say it's homogeneous. Even though we know at a molecular level, there's a whole bunch of other stuff in there as well. A heterogeneous mixture is something you can physically see different substances present. So if you're looking down here at a molecular level, the heterogeneous mixture, you can tell that there's a lot of different pure substances mixed in there, but you can clearly see the difference. There's layers upon layers, difference that you can physically see. An example of that would be like sand. If you ever hold sand in your hand, you know, hey, there's a lot of different colors, there's a lot of different shapes. And in fact, if you zoom in on it with a microscope, you get this really beautiful image of what sand is up close. And it's actually very different from each other. Heterogeneous mixture is when you can actually see the different substances present. Going back to the example that I had before with my marshmallows and my gummy bears, that would be a heterogeneous mixture as well. So let's try it. If we're going to look at some heterogeneous and homogeneous mixtures, let's try ketchup. If you've got a bottle of ketchup and you read the back, you see that the ingredients say tomato concentrate, distilled vinegar, cane sugar, onion powder, salt, all those good things that are inside your yummy, yummy ketchup. But can you see the individual grains of salt? Can you see all the spices? Can you see the sugar? All with the naked eye? No, of course not. You just see red ketchup. Delicious red ketchup to put on your hamburger or your hot dog, right? That means that this would have to be an example of a homogeneous mixture. It looks the same throughout to the naked eye. However, if we were going to look at what my husband packs for lunch every day, and that would be like all of these little nuts in here. So we've got hazelnuts, walnuts, cashews at the bottom floating around in there. We've got a mixture where you can physically see the difference in what's in there. They're all nuts. They're different substances. I could pick them out and have a pure substance of each, a pure substance of hazelnuts, pure substance of cashews. And since we can separate these all out, and since we can see that there's a difference between them within the mixture, we would call this a heterogeneous mixture, similar to the sand that we talked about earlier. You should hopefully be able to now, at this point, test yourself on these different terms. You should recall physical properties and chemical properties, physical and chemical changes, pure substances, and mixtures. Please think about the answer to why sweat evaporating off your skin is a physical change. Think about explaining why your farts are considered to be a chemical change or a chemical property. And also think about identifying chemical and physical changes for each of the pictures behind me. So if you can look at each one of those pictures and confidently state whether that's chemical or physical, you're in pretty good shape. Thanks for watching.
When the thing went quack, 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 you man were ducking.